Okay, you're hanging with Hussick once again. This time we're going to look at covalent Lewis structures. Alright, so these are the categories of Lewis structures we can make for covalent compounds. And just to put it in context, we're talking about models that we can draw, a standardized form of modeling that we use in chemistry to show where the covalent bonds are in covalently bonded compounds. And remember that covalently bonded compounds are always those compounds made between a metal and a non-metal and a non-metal. Okay, so we're looking at the bonds that are made between two non-metal atoms, and the categories for these Lewis structures are basically threefold. So first of all, we have your what we might as well call your typical Lewis structures. Okay, so we've got your basic structures that follow the rules we expect. Okay, and I'll go through the rules on the next slide of what those rules are for making Lewis structures, but they obey what we call the octet rule. And the octet rule is written here. The octet rule says that atoms are stable with a full valence, a little typo there, with a full valence of 8, which means that they're going to have 8 electrons in their outermost energy level. And so that means in their highest S and P sublevels, they want to have 2 in the S and 6 in the P for a full valence of 8. Now the exception to that is if the outermost energy level is N equals 1, like it is for hydrogen, then the valence is full with only 2 electrons, because in N equals 1 we only have an S orbital and it's filled with 2. So generally, most Lewis structures will follow the first example. They'll be what I would call your more typical type Lewis structures. Okay, but we also have to watch out for, and we will see the second type, which are expanded valences. Okay, so for expanded valences, what we're going to find is that the octet rule is not followed. There are more than 8 electrons around the central atom, or it could be what we call an incomplete octet, which means there's less than 8 in the central atom's valence. Okay, so we could have these ones that are kind of exceptions, and then the third category of covalent Lewis structures we need to watch out for are what we call resonance structures. These are structures or models that represent the fact that there's more than one potentially correct Lewis structure. So it kind of exists as both. It actually demonstrates a feature called delocalized electrons, where they kind of exist in both places at once. But what we draw for the model is we draw resonance structures representing the two or three conventional options for where those electrons should go. So I'll show you all four situations: typical, expanded, incomplete, and resonance. Alright, so for a typical Lewis structure, these are the basic rules to figuring it out. And we'll go through this with the example of CH4, methane molecule. So first we're going to determine the number of valence electrons. So for this, you ultimately need the periodic table. Okay, so you need to be able to look up each atom in the compound on the periodic table and see that, for example, for carbon, it has 6 total electrons. 4 of them are in its highest energy level, so it's going to have 4 valence electrons. And hydrogen has 1 valence electron. There's 4 hydrogen atoms, so that's a total of 8 valence electrons, right? So next, we ask ourselves, if each atom has a full octet, how many electrons is that? And we'd see that carbon, if it has a full octet, would have 8. Hydrogen, if it had a full octet, would have 2. And there's 4 hydrogens, so that's 8 for a total of 16 if they were all full. Okay, so this is kind of a theoretical number. Then step 3, you subtract the valence electrons that you found in number 1 from the all full electron number that you found in number 2, and that gives you the number of bonding electrons. Okay, so we would do 16 minus 8 for 8 bonding electrons. Bonding electrons always come in pairs. Okay, and so if we do that number of bonding electrons divided by 2, we're going to find out that we have 8 bond pair electrons. So we have 8 bond pairs. So then we're going to position those around a logical central atom. So we have carbon is going to be our central atom here. And how would you know that? Well, there's a couple of rules. One, you just go with the one that's in the least number, because you know it's going to be the middle. Or you go with the one that's going to make the most bonds, which is like always carbon. Or you go with the one that's the least electronegative. So you'll figure it out. But you put carbon in the middle, put 4 bonds around it with sticks like this. Okay, and I just can't quite fit my 4th one in here. Just a sec. There we go. Put your 4th one in, and then you're going to position those other atoms around it. Okay, and then finally, in step 4, subtract the bond pair electrons from the valence electrons, the total valence electrons, to get the total lone electrons. And in this case, it's 8 minus 8. There are no lone electrons. Or in other words, there are 0 lone pairs in this case. And so, for this particular molecule, CH4, that is the correct Lewis structure drawn right there. I'll show you a few more. What you can also verify for yourself is if you examine around each atom, it should have a full octet. And so if you count the electrons that all kind of belong to carbon here, there's 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Okay, remember that in each little stick, there's 2 electrons, okay? So they all count as being a part of carbon. If you count what's around hydrogen, right, the little stick counts as 2, so that hydrogen has 2, that hydrogen has 2, that hydrogen has 2, that hydrogen has 2. Hydrogen, because its outermost energy level is just energy level 1, it has a full valence with only 2 electrons. Okay, let's work through a couple of other examples. So CF4. Okay, step 1, find the valence electrons. There's 4 for a carbon. There's 7 for a fluorine. Okay, and there are 4 of them. So that's going to be 28 and 4, which is going to be 32 valence electrons. So very importantly, and I maybe kind of glazed over this part in the last slide, but this is ultimately the number of electrons that you need to make sure you show in the structure. A Lewis structure, by definition, shows all of the valence electrons in the structure. So in the end, we're going to have 32 electrons in that thing. Then we go for the all full number, okay? If they're all full, what are we looking at? Well, the carbon would have 8, and so would all the fluorines. So that's 8 times 5, which is 40. Okay, so if it's all full, it's going to be 40. Then we do that little math of saying, let's find the bonding electrons. 32 subtracted from 40, which is 8 bonding electrons, sorry. 8 bonding electrons divided by 2, because there's 2 electrons in a bond, means there's 4 bond pairs. So we're going to position those 4 bond pairs kind of symmetrically around carbon with the fluorines like this. Okay, so this molecule looks kind of similar to the last one. And in terms of geometry or shape, it is the same as the other one, but of course we have different atoms involved. Okay, now finally we're going to determine our lone electrons. And we know there must be lots of lone electrons because we got to get to 32 here. So what do? We take the number of electrons involved in bonding, which is 8, and we subtract that from the total valence of 32. And that's going to give us our lone electrons. So in this case, it's 24 lone electrons, which if we divide that by 2, because like bond pairs, lone electrons also come in pairs. That's going to be 12 lone pairs. So where are we going to put those 12 lone pairs? Well, we'll distribute them as evenly as we can to satisfy the octet rule for every atom. So 1, 2, 3, 4, 5, 6. So that's 3 bond pairs. 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lone pairs put in, satisfying the octet rule for each of those fluorines. You want to double check it. Why not? Look around the fluorine. You'll see that it has 8. That also has 8. That also has 8. That also has 8. Look around the carbon. It also has 8. And the total number is 32. All right, the Lewis structure for NH3 doesn't look like anything special because it doesn't look like incomplete octets that have beryllium or boron. It doesn't look like expanded valence because it's a relatively small central atom of nitrogen. So we can just carry on and proceed. Okay, how many valence electrons in this structure? Nitrogen brings 5 valence electrons. Each hydrogen brings 1 valence electron, and there's 3 of them for a total of 8. Okay, so we need to represent 8 electrons in the total structure at the end. How many if they're all full? What if they're all full? Well, now we're going to have 8 for nitrogen. We're going to have 2 for each of those hydrogens, and that's going to be a total of 14 electrons. Okay, so 14 minus 8 means we are going to need 6 electrons for bonding. They come in pairs, of course, so that's 3 bond pairs. Okay, so we got to show 3 bond pairs. Now, even without going through that math, maybe naturally you would have arrived at that because you got N in the middle and you got those 3 bond pairs to the hydrogens. Seems pretty straightforward. Now the issue is we need to show 8 valence electrons. So if you do the quick math on that and you say, well, we should have had 8 electrons, but we've actually shown 6 for bonding, then you know we need 2 electrons that are going to be lone pairs, which means we need 1 lone pair. Okay, where's that lone pair going to go? Well, naturally it's going to go on the central nitrogen, because if you count around nitrogen then, it's going to give nitrogen that full valence of 8. So you got 2, 4, 6, 8. And so nitrogen's happy. Each hydrogen has 2 around it. This is a stable Lewis structure for NH3, which is ammonia. Okay, here's another example. Again, looks like a typical one. Doesn't look like anything anomalous or incomplete or expanded valence. It has carbon as the central atom. Carbon is fairly typical. So you could start by saying, well, I know it's going to be carbon with these 2 around it. And then we'll just count valence electrons and figure the whole thing out as we do. So the valence electrons in this one are each carbon brings a 4 and each oxygen brings 6. There's 2 of them. 12 plus 4 is 16 valence electrons. Okay, so we need to show a total of 16 electrons. If they're all full, then it's going to be 8 times 3. Each one would have 8 for 24 electrons. Okay, so how many electrons are going to be involved in bonding? 24 minus 16 means there's going to be 8 electrons involved in bonding, which means there's going to be 4 bond pairs. So we need to make 4 bond pairs. Okay, so how are we going to do this? Well, we have over here in the ongoing structure, we've got 2 bond pairs, but we're going to have to add an extra bond pair on each side around the carbon. That's the only way to do it. And this is something that's acceptable to do. These are called double bonds. So each one respectively is called a double bond. So that's a double bond and that's a double bond. And it's okay for carbon because carbon likes to make 4 bonding pairs. Okay, so that's generally what it likes to do. Now to figure out the lone pair electrons, we take the total valence of 16. We subtract those which are involved in bonding, which is 8 of them. And that gives us that we need 8 bonding electrons for a total of 4 lone pairs. So we're going to add 4 lone pairs. And we're going to add them 1, 2, 3, 4 around the oxygens. And the reason for that is because that is going to satisfy the octet rule for those 2 oxygens. Okay? So again, you can check for yourself. You can look around each one. Does carbon have its octet rule satisfied? 2, let me just switch to a pen that I can highlight with. 2, 4, 6, 8. Okay, so it's satisfied. And then check again for oxygen. 2, 4, 6, 8. 2, 4, 6, 8. And so it's satisfied as well. So this is the Lewis structure for CO2. We see double bonds in that structure. Okay, moving quickly now, we're going to go through this one, HCN, all right, because it introduces something called the triple bond, and I'll show you how that happens. Again, you would probably start with the skeleton framework of carbon being the central atom. If carbon's involved, it's almost certainly the central atom. Again, generally what you go to is the one that's the least electronegative, which in this case between carbon and nitrogen will be carbon. And you say, let's count the valence. Let's count the valence. It's going to be 1 for hydrogen. It's going to be 4 for carbon. And it's going to be 5 for nitrogen for a total of 10. Okay, if they're all full, we're going to have 8 times 2, and then we're going to have an additional 2 for the hydrogen. 16, that's 18. 18 minus 10 gives you 8 for 4 bonding pairs. So 4 bonding pairs, what are we going to do? Well, we can't add it on the left-hand side between carbon and hydrogen because hydrogen can only make 1 bond. So we have to add both of them on the right-hand side. And actually, this also satisfies nitrogen's desire to make 3 bonds. Nitrogen, of course, would like to make 3 bonds with all of its single unpaired electrons so that it has a full valence of 8. Now let's check, have we shown all 10 electrons in the mix? Well, we actually haven't. We've only shown 8. And if you figure that out by doing the math here, 10 minus 8 means we need 2 lone electrons, meaning we need 1 lone pair. That lone pair is going to exist on the nitrogen there. Reason for that, if you look, the carbon was already full with all of its 8 electrons here. See, it already had 8 in its valence. Hydrogen was happy with just the 2 in its valence, and so the nitrogen needed those to have 2, 4, 6, 8 in its valence. And that's the stable structure for HCN hydrogen cyanide. Okay, let's get to some alternative structures. So if you have one like this, O3, now it's not expanded valence, it's not like an S atom or a P atom or a xenon atom or any large central atom below row 3. So it looks like a typical smaller central atom in oxygen. It's also not an incomplete octet because it's not boron or beryllium. So let's just rock on and see what happens. I can tell you that it's non-cyclic. That's the first thing I can tell you. So in other words, if you're thinking about maybe it goes like this in a circle, and no, it doesn't do that, okay? So we're not going to deal with cyclics in this course, so you can forget about things being cyclical. What it's more likely to be is something where the oxygens are bonded in a strand like this. But let's take a look and justify that on our own here. So the valence electron is going to be 6 for each oxygen for a total of 18. So we're going to have to show 18 electrons in the structure. If they're all full, that's going to be 8 times 3 for 24. So for bonding, it's going to be 24 minus 18 equals 6 electrons. That's going to be 3 bond pairs, okay? So 3 bond pairs. We run into an issue here. Where do you put the bond pair? Do you put it over here on the right, or do you put it over here on the left, like this? Well, wouldn't they be the exact same thing if you flip it around? Yeah, in a way. But remember, if you label these like 1, 2, 3, you would have to say in the end the double bond is between oxygen 2 and 3, or it's between oxygen 1 and 2. You have to pick one or the other. So what's the answer? Well, the answer is it exists in both places at the same time. It's what we call a resonance structure. Okay, so it has a resonance structure. That means like if it's a 50-50 toss-up between 2 locations, or maybe it's a 1/3, 1/3, 1/3 toss-up between 3 locations for a bond, you go ahead and just propose that, well, it could exist in all of those places at the same time. And so that's the way we're going to write it, okay? So it is the standard format for writing that is to have the double-headed arrow between the structures, and you often also see square brackets, especially if it is an ion. I'm not totally certain you have to put square brackets if it's not an ion, but anyways, I'll roll with it for now. Okay, so we've got our 3 bond pairs. We need to show 18 valence. So how many lone pairs do we have to put in? Well, we're going to subtract 6 from that. We're going to get 12 lone pair electrons. That means we need 6 lone pairs added. Where to add the 6? Well, in the first structure, we're going to just put 1 around that oxygen. That satisfies its octet. We're going to put 1, 2 of those pairs around this oxygen, satisfying its octet for 3, and then the other 3, 4, 5, 6 we're going to put around this oxygen to satisfy its. And then we're doing a similar thing down here, 2, 3, 4, 5, 6, okay? To show that those are the 2 possible structures. And so to get full marks and to present the proper right answer on this one, you have to basically show this whole thing, what's in the red box here. You have to show both structures with the double-headed arrow between them filled out properly as resonance structures. Okay, now let's get into some that are a little bit wilder. So, what if I presented one to you like this? PCl5. Now, for this one, remember your basic idea is like central atom and everything bonded around it with one bond. But you hit an immediate problem here, right? And that is that there's 5 things bonded to the central atom of phosphorus, which means that if we count the valence electrons around phosphorus, it's 2, 4, 6, 8, 10. What the devil is going on here? Well, this is a case of expanded valence. And you need to recognize expanded valence when it happens. How do you know which ones can do expanded valence? Well, basically, it's the ones over here in this area that are larger. So you've got your first row. Oh, maybe I didn't do that very well. There we go. Let's add a row. You've got your first row, your second row, and your third row, known as periods on the periodic table. It has to be ones in the third row or lower. So that's going to be things like phosphorus, sulfur, and then it could be chlorine, iodine. I think I did that backwards. Chlorine, bromine, iodine, and xenon. Okay, those are going to be your top culprits for potentially doing expanded valence. Okay, so you want to watch out for these guys here. Doesn't happen in the smaller ones up at the top, like nitrogen, oxygen, carbon, etc., that we use most often, but it does happen here. Okay, so it happens in period 3 or larger atoms, and it can happen, I should say. It doesn't always happen, but it can happen, really. Okay, so if we look at this expanded valence, remember that the rules now for this, if we know it's expanded valence, the rules don't work so well. Okay, instead we just have to follow the basic rule of Lewis structures, which is that we are showing all the valence electrons. So let's make sure we represent all the valence electrons. How many valence electrons are supposed to be in the structure? Well, phosphorus would bring 5, and chlorine would bring 7, and there's 5 chlorines. That's 35 and 5 for 40 electrons. So we have to make sure we show 40 electrons. We currently have shown 10, right? So we need 30 more electrons. We need to add 30 over 2. We need to add 15 lone pairs to this thing. Okay, let's add 15 lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that fills everything out. Every chlorine has a full octet. The phosphorus has an expanded octet of 10, but in this case, that's going to work for phosphorus. If you want to know why, it's because phosphorus has 5 electrons to begin with. Remember, we said that here. It's got 5 electrons to begin with. It can share each of those 5, potentially, and because it has a larger nucleus, it has enough protons to hang on to those extra negative charge electrons in its valence. And another one where we can kind of throw the rules out the window because it's something pretty special, and that is BCl3. We have a tiny central atom, okay, and if it's boron or beryllium, these are the 2 main guys to look at. Apparently, it could also include aluminum, but usually it's one of these guys, okay? They're really small, right? They're in the first group or second row, second period, so they're really small. And they can be stable without a full valence. This is what we call an incomplete octet, okay, or incomplete valence. So they're going to be stable with, in this case, boron can be stable with just 6 electrons around it. If you put boron as a central atom, put all 3 chlorines, there's really no alternative structure for this. It has to be this, right? So once again, follow the basic principle of Lewis structures in that it has to show all the valence electrons. How many valence electrons does a boron atom bring? Well, it brings 3, okay. And how many does each chlorine atom bring? Well, chlorine atom brings 7, okay, for a total of 21 and 3 for 24. So we're going to show 24 electrons. We've already shown 6, so we got to have 18 extra lone electrons. We got to have 9 lone pairs, okay? And here they go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ta-da! 6 atoms, 6 electrons around that central atom boron. Still stable, incomplete octet. Okay, remember guys, practice makes perfect. I've put out quite a bit. You can find lots of practice out there doing Lewis structures. You just have to watch out for incomplete octets, expanded valence, and resonance structures. Hope this was helpful.